had a chance to visit Rabbit Utopia, where we start off with 1,000 rabbits a year and has all the food it needs, all the resources it needs, no predators, and they just are very happy bunnies, creating new bunnies. Okay, so we start off with 1,000, and in our first table, each year, how is the population changing? By 1,000, and that stays the same from year to year. That's your first key that this is a linear function because you are growing at a constant rate of change by a constant number from year to year. So we see that when we look at the change in T is an incremental change, a unit change of 1 from year to year. And our population's changing at by a constant number, 1,000 rabbits to 1 year. Okay. So anytime we see for a unit change or any, constant change in our independent variable, the same constant change in our dependent variable, we know we have a linear function. We know that the function for this is some number, our constant rate of change at 1,000 in this case, times our independent variable t, and our initial population is 1,000. Remember, we could also write this, it doesn't change, to say I'm going to start off as 1,000 and then grow each year. If you ever notice in your graphing calculator under linear regression, they have both of these models. This first one is more the algebraic model, what you see when you look at a linear function. You're used to seeing mx plus b, but in statistics and in lots of situations with real data, we always put where we start first. I'm starting with 1,000 rabbits. That's what we call the y-intercept. In this case, it would be the p-intercept. And then you see how much to add each year after that. So it's the same exact equation. It just depends on how you're looking at it, Ken. It doesn't change if you have times 1t, because 1t is t, so that's okay. Any other questions? Okay, so now we go down, and now our rabbit population, instead of growing by this constant number every year, it's doubling. So first I tried to sort of have you find the pattern for what the formula is going to be. This is your initial value. Anytime t is 0 or your independent variable, whatever it happens to be, is 0, we call this amount right here your initial amount. In this case, the amount is your initial population. So we could actually fill this in and say, this is my initial rabbit population at the time I start recording, right? So if I'm trying to do a formula and I know it doubles, I know somewhere in here I have to see it times 2. But in this case, for the initial amount, your exponent is 0 because 2 to the 0 power we know is 1, and 1,000 times 1 is 1,000. The next year, I grew by a factor of 2, by a multiplication of 2, not by adding anymore. So now my next population can be written as 1,000 times 2 to the first power. This is very similar to what we did on Monday. Second one is 1,000 times 2 to the second power. There's your 4,000. So now if we were trying to examine this table and we were trying to figure out, would this be linear? What we would do is the same thing we did up above. We notice that the change in t is increasing by 1 year. But when we look at our population change, whoops, sorry, that first one should be 1,000. When we look at our population change, it's the growth in my population is not staying the same from year to year. It's not increasing by 1,000. In fact, what's staying the same is the ratio between the two populations, consecutive populations. So 2,000 and 1,000 is the number 2. It's a constant ratio. It's a constant factor, a constant percentage. That's 100% growth. 4,000 to 2,000 is 2. 8,000 to 4,000 is 2. 16,000 to 18,000. So consecutive populations, if I look at their ratio, I get a constant factor. That's what stays the same. Versus a linear, I get a constant number from year to year that I either add or subtract. If I was looking at depreciation versus growth, it would be a number that would be subtracted versus added. So writing it in this form helped you to find the base, which is 2. How do you get the base? You get the base when you have a unit increase, and you just take the ratio of consecutive populations here. If I had my unit increase being, say, every 5 years, I couldn't get my base that way. We'll see how to do this in a little bit. But because I have a unit increase, I just take the consecutive ratios, and they all come out to be 2 to 1. So that's how I know my base is 2. My initial population now is a number that's out front of my exponential. And now my independent variable's an exponent, which is very different than anything we've looked at so far. Any questions on how to get the equation from looking at the pattern we established in the table? Any questions? Okay. Then I just gave you 3 fictional cities. The ones that are growing exponentially are the ones that have a base with t as a power, and that's B and C. A is a linear model where you start off with 300,000. So the city's initial population is 300,000. And it's growing by 1.3. That's your slope, but it's not 1.3 people to 1. It's 1.3, look at your units, 1,000 every year. Okay, so in city A, we would start off with 300,000. Let's say that would be for time t equals 0. And at time t equals 1, how many people would I have the next year? Just add 1.3 thousand, right? So there we go. It would be 1,300 people. And we would just keep adding this constant number from one year to the next. Okay. So the initial population of city A is not 300. You can either write 300,000 or you could write the number 300, but after it put thousands. Remember, your units are very important, especially when we're talking about population sizes. We often don't put a number like in millions with units. In each individual person, we put it as per million, per thousand, per 100,000. Okay, I would know what it is. That would be fine. That tells me you're at least thinking about what the unit is. Yeah. City B, it's 270,000 if you want the unit to be individual people, or 270,000s. Just depends on how you want to see it. And then you could put 600,000 or 600 with thousands after it. Okay. So Cities A's initial population is 300,000 and it's growing by 1.3 thousand. Or if you, again, you want to put it in single people, you could say 1,300 each year. That's 1.3 thousand. City B, the population is 270,000 and it's growing by 2.1% annually. That's the growth rate. This is the growth rate. Does anybody know how Jasper got 2.1% from looking at this particular equation up here? Does anybody know how we got the 2.1% map? Okay, there's a couple of ways of looking at that. So let's take a look at how Matt thinks about it. Matt says my base here is 1.021, which corresponds to the percentage 102.1%. So he says 102.1% is 2.1% more than 100%. So that's the growth rate. So he compares his full base, he changes it to a percentage, and then he says, okay, if I subtract 100% from that, what am I left with? I'm left with 2.1%. So he changes everything to percentages and goes from there, subtracting the 100%. How else could we get it? That's one way that works fine. Jasper, how did you actually do it?
Well, I know that the 1 equals 100%.
Yeah.
So I knew that everything past the decimal.
Okay. So Jasper says, I know that 1 represents 100%. So what's beyond that 1, the 0.021 represents the growth rate. And so he changed that to a decimal. Yeah. And did anybody, when they did this, actually use the little formula I gave you that does sort of both of these? No, nobody. Okay. Well, let's take a look at it just in case you want something. Remember, we call 1.21 the base. So the base is equal to 1 plus r. This is what both Matt and Jasper did. Matt just said it's 100% plus the rate as a percentage. That's how he thought about it. And Jasper said, okay, I know the 1 here represents the 100%. So whatever is the number that's the decimal after it is the value for r, 0.021, and then he converts it. So there's lots of different approaches to this. So the base is 1 plus r. So if we're trying to solve this equation for r, what would this equation look like if we solve it for r instead of b? b minus 1, right. b minus 1 is equal to your rate. So you look at your equation up here. b is 1.021. When you subtract 1 from that, you're left with just the decimal portion, which is what Jasper said, and Matt, he just converts it to percentages. So that's equivalent to 2.1%. Okay, so that's the growth rate when you look at this exponential function. Okay. So how would we actually figure out if I asked you to do a little table now? We have this formula, 270 times 1.021 to the t. And if I have 270 as my population, my initial population at time 0, how would I get my next value for my population the next year? What would I do? I could put this value in for t, yep. And when I put a 1 in here, what does this become? 270 times 1.021, right? So you just multiply to get the next population, you just multiply by that base, 1.021. Okay, so here you're not adding the same amount. Your amount is increasing by a constant factor, which is a multiplicative idea versus an additive idea. That's right. If you have the previous one. If not, if I asked you for what's the population in 10 years, you would just use the formula. Yeah. Okay. That's right. If it was 2, you put a 2 here, you would square this number and multiply it by 270. Yep. Okay, so the last one, Mahendra said, I don't think I got it right. And why did you have that feeling, Mahendra? It's too big, yeah. Like he's thinking, oh gosh, this would be growing at 100%. That's almost like the doubling of the rabbits. What else should give a hint here when you look at this particular formula for city C that it's not growing, Nick? It's less than 1. In fact, it's between 0 and 1, right? We want to be a little more specific because we'll never have a negative base. Remember, our base for all our exponential functions is always positive. So whenever we see a decimal between 0 and 1, we know in this case our population's declining. It's getting smaller and smaller. And there are a couple of countries, if you look at countries' growth rates, where we have a decline in population. Germany is one of them. And what that means is you have people dying at a faster rate than being born. Okay, but most countries have a positive growth rate. Jasper?
In terms of like, well, this is kind of like, I was thinking of something that would be negative.
Yep.
And I was thinking like, radiation.
Yes. Yep. the mass. Yeah, we're actually going to look at that maybe 2 classes after our next test. We'll be looking at radioactive decay. Yeah, that's absolutely. No. Yes, that's coming up. Okay, so let's stick with city C. And so city C starts with initial population of 600, right? Starting population of 600,000 people, and the population is decreasing at a rate of, now we got to be careful. What rate is it? Okay, remember R is B takeaway 1. So B here is 0.978. So I put in 0.978, and when I subtract 1 from it, notice your rate, your value for R is negative, which makes sense if you're declining. So R equals 0.022, negative. Okay? That tells you that you have a decay, an exponential decay function versus an exponential growth. So it's and since I have this word decreasing rate here, if I'm writing it out and I use the word decreasing, when I write what my rate is, I don't put the negative in front of it. So I would say it's decreasing at the rate of 2.2%. If I ask you for the value of R only, you have to put in negative 0.022. If you write out a sentence and interpret it, and you write words like decreasing, declining, then you've already represented that negative sign. So you don't want to put another negative, because that would be like a double negative, which would mean it's growing. So you want to be careful. That's still increase. Yeah, but that's not decreasing. Increasing at a negative rate is a decrease. All right, so you want to say the population's increasing at the rate? You could. Yeah, you could. Yeah, you just wanted to be what? Oh, you're being a smartass. That's all right. I like smartasses. That's fine. Okay, and this is going to go on YouTube, and they'll hear me swearing. Oh no. I guess ass is in the dictionary, so it's not bad. Yeah, it is an animal. You're right. So you're a smart animal, Nick. Woohoo! Smart for a donkey. No, decay's fine. It's just when we usually use populations, when we're talking about populations, we would normally use decreasing versus decaying. Yeah, yeah, it does. It sounds, yeah. Oh no. All right, so let's take a look. We're going to continue with this idea, because often you'll see tables. Let's say we had a table of, unfortunately, one of the things that we're going to miss out on, which I think is a really important idea, is because of our last snow day, I had to make the decision to either take away the review for test 3 or take away our final modeling for all types of data, which we would have been able to fit straight lines and quadratics, polynomials, exponentials, logs in something called logistic growth functions. And I think that that's a valuable, I will still give you that lesson if you're interested. I think it's a great lesson, particularly in some of the fields that you're going into. For example, for a lot of business people, they have a course called mathematical modeling. Whole course is on modeling. So one of the things you want to be able to do is you want to be able to look at say a table that has real world data in it. And as you know, we're not going to find the perfect function for it, but we want to find a function that closely models the data. And as you know, sometimes we can have a couple of functions that can model it fairly closely. We make decisions based on what we know about the situation. And again, there is that little statistic called R-square, which helps us to determine the strength of the fit for nonlinear situations. So let's take a look at these tables. This is 2 tables wrapped into one. And if you're looking at a table of real world data, you want to try to figure out, would a line represent this better than, say, a quadratic, or in this case, an exponential? How would I tell whether something would be more of an exponential versus a linear fit. So I'm picking data that is going to have an equation that models it versus some variation. And I also want to point out there is a slight error here in my table that I thought we caught before we printed this out again, but I noticed today that we didn't. So if you would just make this correction in your table, take out this 1728 that's there, and the number that comes after that, the 2197, actually belongs with 35. One of the things we want to do is we want to see, is the independent variable here changing as a constant? Is delta x, that means the change in x, is the change in x constant in each step above as we move across the table? Yes. As we move across the table, the change in x is what? 5, right? So the change in x is 5 as we move across this table. So it's constant. So whatever the situation might be, we're looking at increments of 5, right? As we plot our data. F of x and g of x are two different functions. So let's take a look at f of x first. And it says, what can you tell me about the differences between consecutive values of f of x? Consecutive values. It's not every single change of 1, it's every change of 5 here. So what can you tell me about consecutive values of f of x? Well, we don't know what the unit is. What did you say before that, though, Di? Changing what? By 10, right. So the change in f of x is a constant number, it's 10. So because if we compare successive numbers, consecutive numbers, we see 40 take away 30 is 10, 50 take away 40 is 10, 60 take away 50, etc. is 10. So we notice that for every consecutive value of f of x, there's a difference of 10. It's a constant. Notice 10 is a constant. So in this case, every 5 years, we would be adding 10 to our output. Again, we don't know the situation. We don't know the context of this. Okay, but we do know every 5 years, whatever f is measuring here, it would be increasing by 10. All right, so that takes care of f of x. So let's kind of try to, let's see, can I do this? I was going to say, let's block this out in our mind. I think I can insert, never mind. Okay, there's a little shade, but it would cover the whole thing. Now let's look at consecutive values, and I'm going to erase some of this just so that we don't have too much going on here in our visual field. So let's try to forget about f of x for now. And what I'll do is I'll just try to go like this. Here we go. F of x is gone. All right. What can you tell me about the differences between consecutive values of g of x? Well, let's look at consecutive values of g of x. So g of x here, the consecutive values would be 1300 minus 1000, which is 300. Consecutive values here would be 1690 take away 1300, which is what, 360? And what would it be here? 2197 take away 1690. What is it? Oh, 390, thank you. Yeah, thank you. What about the next consecutive values? Is that right? 507? 507? Okay. And then finally here, you all have your calculators. What is it? 659.1. Okay. So is the change in g of x a constant? No, not a constant. So we know that we would not try to model this data with a linear function, but the first data, yeah, we could model that with a linear function. So the question now is, could we model this data with an exponential? Would that work? So let's see. Exponential. Well, if you have an exponential function, your consecutive changes here, the consecutive ratio of these changes would be constant. You would have a constant factor. So let's see, we've got 1300 to 1000. That's my consecutive values of g of x. So now I'm looking at ratios. Are the ratios the same between consecutive values? So let's see, 1300 divided by 1000 is what? 1.3. Okay. What's the next two? 1690 divided by 1300. Let's see what that is. Is that 1.3 as well? Oh, that's nice. Let's see. 1690. I just want to be sure. It's not that I doubt you, but I want everybody to see how we're getting it. All right. Is 1.3. Okay, let's look at the next two. What would it be? 22,197 divided by 1690. It's the same. 1.3 probably. Let's see. 1690. Yep, that's 1.3 as well. Okay. Now, folks, if our change in x was 1, was a unit increase, then we would know what our base is right now. We could put 1.3 to the x. But it's not a unit increase, it's by 5. What this does tell you is that you could use an exponential function to model this data, or to actually come up with the equation for this data. It's not real world data here. So how would you do that? Well, if we had the initial value here of 0, we could go right to town, but we don't. Or do we? Could we? Matt? No, because it's at 20 versus 0. You could follow it backwards, Abby. That was what we'd have to go back how many times? Once to 15, another time to 10, another time to 5. We'd have to go back 4 consecutive times. I'd rather wait till we get a little bit of data like in the first class activity. We can do it quicker, just for the effect. All right, so this consecutive differences is not constant, but consecutive ratios are. So this is going to be an exponential function. No, it's not persons. Did you say persons or percent? No, it's not percent, because this is not change in x of 1. If it was a unit increase, Mahendra, then it would be growing at the rate of 30%. Well, I don't know. I don't think it works that way. We'll see in a minute. Okay. So just coming back to our rabbit population example, when we see a linear function like this, 1,000 plus 1,000t, the growth of a linear function is additive. Even when it's a negative number, you can still say additive because you're just adding a negative number. This means that for each year that passes, we add 1,000 to the number of rabbits. In this example where we were doubling, we say the growth of an exponential function is multiplicative, right? We know that we can multiply by a number, in this case 2, to get the number of rabbits from one year to the next. So in general, this is how we would write a linear function, and this is how we would write an exponential function. So this is an important idea here. I would ask that you highlight it right here. You'll see this in project 4 when you get it. Exponential functions represents quantities that are multiplied by a constant factor for each unit increase. And that's why we couldn't deal with the table above in the same way we could with the rabbits, because it wasn't an increase. Change in x wasn't 1, it was 5. So we're gonna start the class activities together, and I want to show you. My other class wasn't really interested, but I know this class is different. I didn't give them the option. I didn't do it with them. So let's talk about this first table. It's very similar to what we just did, but what I'd like to do with you is to find the equation for the exponential function. Once we determine here whether f is the exponential function or whether g is the exponential function. So why don't you do that first together or separately, individually at your tables. And when your table is determined which is the linear function and which is the exponential, just put up your flag, and then we'll find the formula for the exponential function. Okay, so is the change in x constant at each step? If so, what is it? 10. Okay, now, as you know, in many of your class activities, Caitlin and I choose to continue to introduce new information. Okay, and this step 2 here has some really important ideas, these two sentences. The data are linear when the difference between successive outputs or y values is constant. Okay, we noticed that in the example we did in the class demo. So that's the kind of thing you should make sure you have in your notes or in your head or somewhere. Data are exponential when the ratio of successive y values is constant. So we were just looking at that a second ago. But we have not yet learned how to take that information and create an equation for exponentials, unless it had a change in x of 1, which we don't have here. So we notice that f is changing by 30 as we move every 10 years. If we were looking at time, we could say every decade something's increasing by 10 something. We don't know what the units are. So f of x was the linear because the differences between successive outputs and f was 30. It was a constant number. What you notice I heard you talking about is that in g of x, the ratio between successive values of g of x, this ratio was 3 to 2. So the ratio was constant between consecutive values if we go throughout this whole table. So g of x is the exponential function. Now, unfortunately, we can't say g of x is some initial amount and the base is 3/2 or 1.5 raised to the x. It would be nice if it was that easy, but it isn't. So let's take a look at, if you had this data, how would you find an exponential function for it? So I'm just going to go over to the next page. I blocked out f of x so it doesn't confuse us. We know that our consecutive ratio is 3 to 2. Our change in x is 10. Okay. So what I want to come up with is some function for g that has that formula, the form that we talked about initially. It's the initial amount times some either growth factor, in this case it's a growth factor, raised to the power of x. Okay. So with this table versus the other one we had for the class demo, we have something sort of given to us. We have a gift. Can anybody see what our gift is here? No, we don't know the growth factor yet. We think 3/2 is a growth factor, but remember, the change in x is in a unit increase of 1, so we can't use that in here yet. Matt? We have the initial amount, right? When x is 0, look, g of 0 equals what? Whatever this b is here, right? Whatever it is, we know it's 20, right? The initial value is 20. G of 0 is 20. So b to the 0, whatever our base is 1. So we know it's 20. So that's our little gift here. That gives us part of our equation. We now have part of the equation we need. G of x is going to be 20 times b to the x. Now the big deal is, how do we find b? Yeah, Jasper? Yeah. Okay, so What do you want me to change?
So if you knew that 20 is 0, and if you change your
0,
initial,
20.
sure, so,
Yep.
and then let's say you put in 30 for your initial set 20, and you found that
Found what?
more like 30 for your initial,
Okay.
but so if like you put in 30 for 20, you put in 0 for X.
I can't put 30 in for 20 because this never changes the initial amount. But that's a good, you're on the right track, so to speak.
So it's 30 times,
All right, so let's try this because I think that this is sort of what we intuitively think is going to work. All right, so what you intuitively think is going to work, let's try it out. What you intuitively think is that, like with slopes, you can take this thing, which is not an additive thing, it's a factor that it's growing by, a constant factor, and you like to divide it by change in x. Let's try it. If we had 3/2 divided by 10, it would be 1.5 divided by 10, which is what, 0.15. So are you saying the base is 0.15? Oh, 1.15. You think it's 1.15. Okay. So I think it's really good to go with what you intuitively feel and see if it works. So let's try it because this is what, can we stop talking, please? Thank you. So it's 20. So not Jasper, Spence is hypothesizing. It's an educated guess that it's 1.15 to the x. How could we check if this is correct? If we put a 0 in for x, it doesn't matter what the base is, our answer is going to be 20. So the 0 point's not going to help us to determine if it's correct. What could we do to see if this is equation for the data we have up here in the table? What could we do? Yeah, let's try 10. When x is 10, what's my output? Look at your table. When x is 10, 30. Okay, so that means I put a 30 here and I put a 10 here and I check it with my calculator because this is what we really want to do. Let's see. Let's see if this is right, and if it is, woohoo, we've got a really easy way of figuring out our exponential. So let's try it. 20, wah, wah, let's try it. 20 times 1.15 raised to the 10th power. Let's see if it gives us the golden 30. Oh, it's way too big. Shucks. That would have been nice, right, if it worked? All right, so I just gave you a little hint as to how to approach this, and you didn't even recognize it as we did it. So that doesn't work. What? Nope, that doesn't work either. Yep. Yep. Yes. Let's do it. Yep, you got it. It's what I've been trying to say over and over and over again since we started with linear functions. If we find the slope of a line and we have the equation, here's our little side note, we have this for an equation, and we're trying to find b, what do? We find a point on the line and plug it in for x and y. Then we solve for b. When we had our quadratic equation and we were trying to solve for the vertex, and we put the vertex in, and we were trying to find the value of the leading coefficient, we put a point in. When we have a polynomial, it gets old. It's the same thing over and over. We have everything we need right in front of us. We're trying to solve this equation for b. Do we have an x value and its corresponding y value or output value anywhere? Yeah, we've got 1, 2, 3, 4 of them. So plug it in. Plug in any one of those 4 points other than the one we used to find the initial value. So let's use 10, 30. So I'm going to put the 30 in for, because 30 is g of 10. That's the output when x is 10. Okay. Now you may not believe it when we do it, but this is how it works. Now we can solve for b. How am I going to solve that equation for b? What do I do to both sides first? Divide by what? 20. I'm going to divide both sides by 20 to isolate my variable. Do you see the 3/2? There's your 3/2. But it's not 3/2 divided by 10. It's not 2/3 divided by 10. It's 3/2 represents your base raised to the 10th power. So how do I undo this? How do I undo raising something to the 10th power? Huh? 10th root of both sides. That equals B. So let's take the 10th root of both sides. Your calculator can do it. We can't do it, but our calculator can. So remember that the easiest way to write this in the calculator is to make 3/2 1.5. And what is the 10th root as an exponent? Nope, not -10. That would be 1 over 3/2, 1 over 10, right? Which is the same as what decimal? 1/10. 0.1. So I'm just going to use my calculator right now, and I'm going to put 1.5 in, and I'm going to raise it to the 0.1 power. That's the 10th root. And there I am. That's my base. My base is, if I write it out in all of its glory, well, you can't do it all because it keeps going. But I have enough of it. Whoa. So if we look at that, base, what's the rate of growth? What's the rate of growth? The base is 1.0413. What is the rate? What is the value for R? No, it is not 1.4. 4.1379 blah, blah, blah percent. Okay, so you may not believe it, so let's try it. This is the base. So let's put in some of our values here. Let's put this equation into our calculator. 1.04 blah, blah, blah. Well, my equation knows the whole thing. So I'm going to say take the second answer, which is that number right there. I'm going to raise it to, let's try another point. What was the next point after 10? It was 20, right? I'm going to raise it to the 20th power. And then I'm going to take all of that and I'm going to multiply it. Oops, I don't want, I got to put that in parentheses. Let's see. I'm going to do it this way first. 20 times, let's see if it'll take my second answer now. Yeah, my second answer, which is this thing, 1.04, raised to the 0.1 power. Nope. What are we raising it to? We're raising it to the 20th. No, we're raising it to the 20th because we used the 0.1 to get this answer. So what's your table say is the value, the output value when it's 20? 45. So remember, what's sitting right here is the base, 1.041379744. We're raising it to the 20th power because that's the value of x. This happens to be our initial value as well. Let's see if we get 45. Closing my eyes. 45, okay. So that's how you get the base when you have a data table for your exponential function. It's no different than what you've been doing forever. You find the initial value, that's your key, and then you say to find B, I got to plug in 1 point from this equation that fits one solution. So you put a 10 here and a 30 there, and you solve your equation, and you get B. All right, I thought I'd show you that. I thought you'd be interested. I think it's kind of cool. Anyway, you can keep going with your equation, your activity.